Thank you all for coming. I know it's the last day of the conference. Are we having fun yet?
Yeah.
Yeah? Excellent. Right, so the original title of my talk was What I Talk About When I Talk About Cross-Platform Development. That's inspired by a Murakami book called What I Talk About When I Talk About Running on Multiple Platforms. But they asked me to change it to the more vegan, unfriendly, the Salami Method for cross-platform development. So anyway, I'm a software architect. I do a lot of computer vision, machine learning, consulting, training, and I am the organizer of the core C++ users group. So the first question that comes to mind is, what is cross-platform, right? Because these days, one project or one product may need to target multiple different platforms. And even if you don't often actually think you need to do that, you might need to do some unit testing or any other kind of testing for your systems and do that on different platforms than the ones that the product is actually targeting, or simulations. And there are many levels and different types of platform. So the closest to the hardware, we might have custom designed chips like ASICs. And then when we start going up, starting moving away from the hardware, we have embedded systems, and we go to mobile. And mobile is a very wide market. It's got at least two popular operating systems, iOS and Android. Each one has its own different ecosystem. When we move to desktops, which have their own different operating systems. And one very common, very important platform that's become a de facto platform in the last couple of months are the browsers. No, I'm joking, several years. So if any of you remember browser plugins, they used to be popular about 20 years ago, and Google tried to do something with native client. Today, JavaScript has been the de facto scripting language of the browsers, and I will mention WebAssembly a little bit later. So the browsers are also still running on some clients' desktop. However, these platforms that we might have to target may actually live in the cloud. And there we're talking about servers. We're talking about Docker images. We're talking about Node.js, serverless systems. And that's not the only things we have. We might also have to start targeting vehicles. Or smart cars, autonomous vehicles, they have their own operating systems. They have their own embedded systems. And we might have to target our systems. Let's say I'm working on some software for an autonomous vehicle. I'm not actually going to run and debug it, all of my code 100% of the time on that hardware. So I do need to test it on some desktop platforms, for example. Similarly, we have IoT devices, robots. We have heterogeneous computing systems like CPUs and GPUs. So you know, at the end of the day, C and C++ are really the only viable languages for doing cross-platform development, because essentially there is no CPU, no piece of silicon made today that can do computing which doesn't come with at least a C compiler, right? So what I'll talk about today doesn't include things like frameworks that somehow abstract a lot of the functionality of each platforms, or things like the virtual machines, which do the same thing. But I'm going to talk about various aspects that apply to whoever writes these frameworks. So, but often you don't have these frameworks available, and you still have to target. I've personally written multiple products and projects that target lots of different subsets of this list, right? So a very common thing when you come to study a new platform is you go to all these popular websites. Who here remembers Code Project? Yeah, fondly, I hope. MSDN, which yesterday I learned is now called Docs, Microsoft, or GitHub, something like that. And of course, if you go and look for Android SDKs or go into iOS, ROS, that's a robot operating system, Qt, they all have these extremely rich libraries, extremely rich SDKs, and significant parts of those SDKs actually duplicate things that you can find in the standard. However, they're kind of a lock-in thing where they want to keep you using those. So if you remember, MFC had all the C arrays and C lists and that kind of thing. So the problem when we're reading that code is that it becomes a refactoring nightmare, because we have to write platform-specific code for each platform that we're targeting. The code becomes unportable, extremely difficult to test because it mixes concerns. It becomes bug-prone, and Another aspect which isn't necessarily the first thing that comes to mind, we have a mixing of skills. So if I have an extremely talented iOS developer, I want to utilize their expertise in maybe in OS X and iOS UI design and not have them touch code which has business logic, which then has to be duplicated in Java for an Android phone. So mixing of skills means that we're underutilizing the resources for our company and the project and our resources, right? So these are all very important aspects that are affected by having this mixture. Then we have issues related to module boundaries, error handling, things might crash our program. So over the last several years, I've developed this kind of methodology for how to structure our project in such a way that makes everything much more transparent and much more easier to maintain, to build, to test, to debug, and manage the code. This is not a magic solution, okay? The ugly platform-specific SDKs will still be there, at least in one part of your program. However, it will be managed, it will be contained in its own layer. What I will show you is basically, and that's the salami analogy here, is that we're going to create a whole bunch of extremely thin and transparent layers, each one representing a different aspect of targeting multiple platforms. And whenever we do have to insert platform-specific code, it's only going to be limited to that particular place where the particular developer who has the skill set to touch that only has to concentrate there and not mess with the rest of the logic. So the benefits that we see from this approach, of course, is the DRI principle. We avoid duplication. I have been involved several years ago with a company called me in. They had a product targeting both iOS and Android, and essentially the iOS team was duplicating the Android team's work. Every time one team found a bug, the other one had to go and try and find it. Of course, it's a totally different code base, totally different language. The apps never behave the same. So we want to reduce the possibility of duplication as far as possible. Similarly, once we are able to separate these concerns, we can have single responsibility, we can have testability. And if we're keeping our slices thin, everything is very transparent. And of course, we want to keep the business logic as far down on these layers as possible. So it's isolated and shared between all of our platforms as much as possible. Some of the extra benefits that we get is that if, maybe Microsoft releases some kind of mobile operating system that somebody actually cares about, our code will be platform ready. No offense to any Microsoft people here. And as I said, developer skills, if we have skilled developers, they can come in and help us put their knowledge and expertise exactly at the point where it's needed. Refactoring of well-separated concerns is always easier. Right. So this essentially, if you had to choose just one slide from this whole talk, this is the slide. Basically, I'm going to walk through this diagram. It looks a bit complicated. In the spirit of C++, I've given each of the slices a very badly named acronym. Okay, you'll see those along the way. Of course, I made up these names. They don't mean too much. It's just to make sure we're understanding. And we can see that at the bottom, we have the cross-platform core. So I'm going to go, and then going up all the way, and at the top level, we're talking about the target applications. So these are the applications that actually run on our target platforms. These are the host applications. And all the layers in between, I will talk about them specifically when we get there. Now, I will say this, and I will say it again later. Very often, it's more practical to merge two of these layers into a single layer. Maybe some aspects of our particular targets don't actually require these multiple implementation of separate layers. However, and I think this is one of the important messages here, all of the aspects that I will be addressing here still exist in your program. So that's something that we have to keep in mind. And in fact, the example that I will show you at the end is going to merge several of these layers because it's an extremely simple program. Right. So at the heart of our system lies the cross-platform C++ core. This is the apple of our eye. This is the IP. This is where all the business logic resides. And it's really the main reason we're actually writing this software to begin with. Right. So this is where we use our idiomatic C++. This is where we use all our design patterns. We're thinking about we're thinking about the design patterns that affect the way our code is structured. The way the modules, everything is beautiful, and it's the kind of thing they teach you here at CppCon, on the books and where you apply it. And the focus is really on the solid, maintainable, well-designed architecture. We're not necessarily thinking about how we're going to interface, because this is all cross-platform builds, very typically a static library, and this is where we can do our unit testing, a lot of functional testing. Everything might be done on multiple platforms, but again, it should be functionally identical. So this is where we're starting our journey. You can see up in the top right corner, we can a small diagram that we saw just before, and we're currently at the lowest level. Now, going up one level, I'm making a distinction for something called the cross-platform public C++ interface. Now, in certain code, this is the public C++ core API that we're going to expose to the consumers of the service that we just implemented. And this is where we apply good API design principles. We focus on the service consumers. And we're also thinking about things like initialization, shutdown, lifetime management, sessions, configuration, serialization, all of these things that make our software not just some kind of algorithm running in the ether, but actually something that has to run somewhere in the real world and interact with reading files, reading JSON or configurations, maybe interacting with the world. It's also a very good place to do things like hiding proprietary code. Maybe the build is really complex for your system, so inside your own organization, you might deliver a static library to another team, and that team can use that only as binary and not actually have the whole complex build. Reducing dependencies, who's familiar with the pimple idiom? Compiler firewall, exactly. So this is the place where this helps, and you're reducing the dependencies your consumers need for your service, right? C++ modules naturally fall into this category. This is where, because by definition, they expose the public interface of the library you're working on. And the type of testing we do at this level, remember, our code, our underlying code is already unit and functionally tested, but here we can start to look at mocking, and we can start to look at unit testing the API itself. So unit testing is actually very important for API design. This is one of its major benefits. And when we're doing the unit testing at this level, we're ensuring that the type of API and the usage idioms that our consumers are going to use makes sense. The type of, there's a comment about naming conventions. So let's say my underlying file was called core CPP, so I generally call it something like core_API. And to make it clear, this for small project, you might actually, and if your design allows it, you might consider skipping this for small projects. So we've now reached the point where we cannot let any more business logic leak out anymore, because this means we're going to have a bifurcation of the logic. So at this point, if we look at the diagram, you see we're on the second layer. And at this point, we don't want any of the business logic. So everything we're going to see now is all about building on top of these underlying smart IP business logic layers, but no business logic. And this is actually one of the biggest fail points that I see in multiple code bases that I come to, that there's an extreme mixture of logic and interface. So you go and you see somebody building a DLL for Windows, and there's a lot of mixing of business logic to get, and maybe conversions and stuff like that with actual algorithms. So this is, the reason I have these blinking lights is because this is from actual experience, right? So no business logic, remember, some target platforms might not actually, my laptop. Some target platforms might not actually be using any additional layers. So if we have, like I mentioned, a C++ API, if we want to put it into iOS, Objective C++, we'll compile C++ files as is, right? So maybe our host app is already using whatever API we provided. Or maybe it's totally cross-platform, so any C++ application can hold that. So it's not just about duplicating business logic, it's about some other platforms are not going to have any additional layers. That's why this is extremely important to prevent this inconsistent behavior. So the next layer is the one I call the cross-platform public C interface. And this is a very, very thin C API wrapper above our public C++ API. Now, you know, the true lingua franca of computing is C. So there, as I said before, there is no hardware, no silicon hardware out there that doesn't have a C compiler. So even if it doesn't have a C++ one, it will have a C compiler. And C has a very stable and simple ABI. It allows linking between different compilers, different builds. And this is extremely important, for example, for inter-language interoperability. So anything can typically load either C binaries, maybe as shared objects or other types of binaries. And the typical thing we see in this layer is the extern C. Essentially, I'll show an example in a minute. This is a good place to do portable type conversions, for example, from string to char star. But here we also need to think about how we manage object lifetime. So because C doesn't have actual objects and we can only pass primitive types, we need to think, do we have just a single global object or a singleton? Otherwise, we have to, the whole opaque handle idiom, which I won't go into here, but that's one additional solution. We have to take care of overloaded C++ functions, where C doesn't allow overloading functions. And again, this is a place to mock and unit test the API itself, the SDK itself. There's a note here. When we actually go to implement the functions, that, as we'll see in a minute, it's an excellent place to immediately lift up these lower level weakly typed types, primitive C types, into some higher, stronger type. So things like std span, std string view are perfect candidates, and that's exactly what they were designed for. So let's see an example, and I'll get into it a little bit more. So we use the extern C for ABI linking. And actually think of these, the extern C, these are like the air quotes, right? Because I'm really talking about C-like standalone function interfaces. As you'll see, let's say I have four functions here. The first one is called init from file name, and it takes a string. So obviously std string is not a C type. We'll see why I did that in a minute, so just bear with me. But another one, init from cow, takes an integer, process buffer takes a pointer to some kind of a character buffer and a size, and a Boolean function. So notice that I have two functions called init, and in fact, in the C code, these correspond to a method called init, but again, C doesn't allow overloading the same name, so we have to give them a new name. So this would be what the C++, the .cpp file might look like. We have, in this case, a single global singleton. I call it, it's the foo session, and there's just one object, the session. In cases where such a global is sufficient, but we don't have default initialization, we might be able to use some an in function or a stud optional or a unique PTR. Now, if we look at the top two functions, we have that we saw in the header, we have init from file name, which takes a string, and it just forwards that down to the member init, and init from count, which forwards the count. So here we see how we resolve the name handling. Process buffer, again, calls session.process, but instead of passing these pointers, a pointer and a size, which are low-level types, very prone to error, a lot of issues. These are exactly the type of issues that std span was designed to solve. So we don't actually use buffer and size except at the point of creating a span. This is a zero-cost. It doesn't, at runtime, it has no effect, but again, it saves us, and session.process, the process method, can actually be safer and less bug prone. Right. So at this point, we basically came to the point where we're still cross-platform in the sense that our system can build with multiple compilers for multiple targets. We haven't used any platform-specific APIs. This is also the place where systems like Mscripton or WebAssembly, Objective-C++, Swig, or even, if any, PyBind 11, this is the place where they can interact with your code. So remember, we said we don't have any business logic beyond that point exactly because of this. Because at this point, we already have the option to target additional platforms which are not going to be part of the rest of the layers, right? So do we have any questions up to here? Yes. Can you go up to the microphone?
A question regarding testing. So I guess you have duplicated tests for XC API and X API. It's quite the same tests, just using different APIs.
Well, if it uses different APIs, it's not the same tests.
I mean, just the same expectations on.
I think of it in the opposite way. I think that by testing, you're actually going through the experience of how your consumer is going to use your API. So by writing these tests, you understand the thought process, and it's also a documentation of how to use the API. So yeah, the C API is separate from the C++ API. Therefore, each one of them needs a separate unit test. But you're not unit testing the functionality of the core algorithm. You're testing the SDK. It's a different type of testing.
Okay, do you have any common code usually in your projects between these two?
Well, you're only testing the API itself, so you can't. You can't have common code. You're calling different functions. Some of them, let's say the C++ might have objects, and you're calling methods. The C interface is basically a call to functions, so there is very little duplication here. Okay. Things like object management are completely different in a C API and a C++ API. So generally, there won't be common code.
Okay, thanks.
Yeah, does that make sense? Great. Right. So we come to the platform boundary interface layer. Now, this is where the nasty code begins, right? So if anyone here has tried to write use a platform-specific SDKs, this is where the nasty stuff comes. But again, as I mentioned before, we can only keep the nasty stuff here. And everything we write here is platform-specific. This is where we perform bidirectional data and type value conversions between the native target platform and the platform agnostic code that we used previously. We have things like strange conventions that we'll see some examples of in a minute. We have to make conversions. This is an excellent place to set up your logging. So even if it's very often a good logging framework is cross-platform, but you can insert some platform-specific backends. So this is where you plug in your platform-specific backend, and the rest of the logging just works. So if my app uses such a framework, on Android it would output to the Android console, and maybe on Windows it would go to the trace of the Visual Studio, for example. This is where we meet the module boundaries, because beyond this wall, there is no more C++. We're leaving this comfortable, cozy world of C or C++, right? So do you know what happens when an exception is thrown from a DLL or a shared object? Yes, it terminates. The program simply dies. So this is where we have to think about the most extreme and unexpected failure conditions. One interesting thing here is the testing. How do you actually test platform-specific code? And I have no answer for that. In fact, I have a Stack Overflow question about that for about 6 years ago. It has no answers. So if you do think of come up with something, do let me know. And in this case, for example, the naming convention, remember, we are now targeting specific platforms. So if I had the Core C API, I might call it Core C API DLL for Windows shared object, or JNI in the case I'm targeting Java or Android. So let's see, continue our example. We had four C functions that we used before. In this case, this is a DLL or a shared object example. We have to prefix the name foo session into the name of the function just because that's what you do. You want to prevent collisions in the DLL namespaces, because DLLs have global namespaces. And we have the DLL export macro. I generally have CMake generate this macro, so it works on all on Linux and Windows and so on. And you can see that the first function, init from foo session underscore init from file name, actually takes a platform-specific string. So that's the LPCSTR character type or string type from Windows. Because again, now I'm wearing the hat of the Windows developer. And this is the API that I'm going to give to a Windows developer, and this is how they expect to process strings. And if we go and look at what the implementation of this file is going to be, it's a little bit a block of text, but it's 90% boilerplate. So we have for each of the 4 functions, we have the same signature. And you can see that the implementation is simply, it's like a trampoline function. It just calls the global C function, right? And the nice thing, you see that the LPC string from Windows is automatically converted to a nested string. And the rest of the conversions just work. Now, I am using something called the function try block syntax, which I like to do for DLLs because it keeps the try catch out of the logic of the function. So the functions appear extremely thin. If you've never seen it before, it means that I can put the try keyword outside of the scope of the function and have the catch out. The try comes before the block and the catch comes after the block. I'll show another example of that in a minute. Yes.
Do you use some solution to auto-generate such code?
I don't. It really depends. It depends on if you have an auto-generator. Again, this is platform specific, so I'm guessing there are such tools. I think Swig does something like that. PyBind is a kind of generator. And if you do have a generator, then you already don't need to implement this because you can already use the API that you had in the previous layer, right? So, yes.
Do you use, like, if you had C++ at this level, do you still go through the C API to get to the lower level? Do you still do that? Or do you have an alternate C++ API, the one that's beneath the C one that you talk to?
I think the answer is yes. In the sense that it's really up to you. It depends on your program. As I said before, sometimes if you're targeting, I'll take a step back. You're looking at the Windows example. And in Windows, we could write a DLL that internally uses C++. And in fact, this is C++ code inside the function, although the functions themselves are C function, are extern C.
Extern C, yeah.
So the API that you design really depends on what platform you're targeting. If I'm targeting something like, let's say, language interoperability that can only handle C APIs, then it's much easier and cleaner to use the C API, not the C++, because otherwise, if I'm using the C++ API, in this case, you can't keep, you see, these are single-line functions. If you start using, so now I have to declare my object. Where is that object going to sit? Okay, maybe I'll put it in the global scope, and now I'm going to start calling the method. So already you're already leaking. You're basically trying to do something that had to be done in the previous layer. So as I said, these aspects I'm talking about will always be there in all of your code. You cannot get away from doing this. All I'm trying to show you is that it's possible to slice these things and separate them. So if you make the decision to make thicker slices, what you're really getting is thicker functions, and you're risking mixing concerns, and you're risking whenever a bug appears. This is extremely easy to debug, or easier to debug.
Sure.
Right.
All right. Thank you.
Okay.
Actually, it's not a question. It's answering to the question about auto-generation. Yes. There is a project driven by Dropbox named dgenie, which can generate like interfaces for C++ and the rest for Python, Java, and Objective-C. So you just need to implement these interfaces, and all magic happens like in auto-generated code.
Okay, there you go. But
just go to GitHub. Find Dropbox account and like dgenie or something like this.
Okay.
And the second is such type of function declaration no except safe. So if I throw exception and no except, can I write no except after before try?
I really don't know. I guess so. I haven't. I mean, this is the DLL, so it's going to be called externally, and you don't. I don't know if it makes any difference in code generation. You're welcome to let me know.
Thank you.
Hey, I'm just curious why you're catching the exceptions here and not in the C API layer, because if a C caller got an exception, that'd be bad as well.
Well, C doesn't handle exceptions. There are no exceptions in the C interface.
Yeah, but in the implementation of the C interface.
You could do that. You could do that. The thing is that you don't necessarily know how you want to handle the exceptions because each platform might decide to handle them differently. Let me show you an example in just a second, okay?
Sure.
One note about exceptions, C API can propagate exception. I mean, you can throw exception in C++ code, then called by C code, and then call again by C++ code, and it will
It's
and
air quoted C.
it will work.
Yes, exactly. Okay, so let's see another example because this is already platform specific code. I have to show you another example of another platform. So this is an Android JNI example. And as you can see, these are very beautiful function signatures, and they have the types and the names must conform to the JNI conventions. As I said, this is where the nasty, ugly code comes in, but this is, we have to do this. There is no way to get around because that's just how JNI is defined. So we have the exact same 4 functions that we've seen before, but this time the signature would be, okay, first of all, we can see the headers. So we have jni.h, that's the JNI headers. We have Android log, which is the logging facilities, our session, and I'll talk about the last one in a second. It's another utility package that we might be able to use. And in this case, you can see that the function, they have this JNI export defined in front of them, and they're already using platform-specific types. So JBoolean, we have JString, JInt, and all of the JNI methods have the first 2 arguments, which is the JNI-env, which is the JVM environment, and the JObject argument. So has anyone here ever written in JNI code? Yeah, okay, so you've all seen this type of code, but doesn't it feel amazing that the functions are just 1 line long, right? I mean, there's no resource management here. Everything is super simple. Now, as for the JNI utils, in this case, you can see in the function Java process buffer, I actually have some kind of, it's an RAI adapter that I can create called the JNI byte array adapter. I create it from the span and then call that, pass that to the process buffer. The destructor is going to do all the resource deallocation, all of the JVM stuff that is usually extremely nasty and bug prone to do manually. Another thing that you can see here, I'm actually, instead of returning some kind of error code, in this case, I'm returning the error value returned by a function called exception handler. And for JNI, I wrote some kind of exception handler that uses an internal throw to recatch the exception. And in fact, we cannot throw an exception inside DLL code. It's going to crash our program. So what it does, it actually opens a new exception on the JVM, copies the string from our C++ exception into the JVM exception, sends that to the Java virtual machine, and just exits from the function code, right? So the nice thing here is that because it's encapsulated in a function, I can have identical exception handling in all of them. Each one, you see, it's just a single call. So again, it's very bug prone to start copying catch clauses between multiple, let's say, sometimes I'm guessing your APIs might not be just 4 functions, they could be 20 functions or 50 functions. We can have a consistent exception handling. Naturally, this is really for the rare cases. You should be handling your exceptions internally in such a way that they don't actually make it this far up. But if they do, at least we know that we're safe. And it's not going to crash our program. Whatever the host app does, that's their responsibility. Yes?
So exception handler is platform specific.
Yes, this is all platform specific code. The only reason I can write an exception handler that can generate an exception a Java exception on the JVM is because I'm in the Java, in the platform-specific code. And you can see these are platform-specific headers. Right. So we're not in Kansas anymore, right? So the native import layer, we went one layer more up. And now we're running on the host app, on our target platform. So this is some kind of, it might be a different hardware, a different device, a different operating system, and very frequently a totally different language. This is not C++. And this is where we have what I kind of ironically call the native interface. Because the word native is actually overloaded twice with opposite meanings. So if you remember, Microsoft had a conference called Going Native where they were talking about C++. But if you think about iOS, then their native language that you write in would be Swift or Objective-C. But then how do they call the code? How does the C# call the code that reads DLL? That's the native interface, right? So actually native is, this is where we're going to use the native interface, which means we're going to use the platform-specific APIs that are used for loading natively generated code. And this is where we're going to essentially create a reflection of the boundary interface layer SDK that we just saw previously. It's typically very low level, very relatively primitive types. The type of testing we can do here is usually target integration tests. So remember, our unit tests already ran. We know functionality should be covered by those tests. But again, we want to target the integration tests. And again, these integration tests are actually running on our target platform. So they have to be, in this case, they do have to be duplicated between different platforms. But again, we're targeting different platforms, and each one may appear differently. So for example, you can see the suggested naming conventions here. The extensions of the file are for C# or JavaScript. We're not in C++ land anymore. So let's see what this might look like for the example we've seen before. This is a direct mapping of the JNI function names on Android. The code for C# is essentially identical to what you see here. And we're using the system load library function, which is the way, this is the native call where we're actually loading a binary DLL into Java. And we're reflecting those JNI C functions that we just wrote into the Java namespace, into the Java type system, right? So we have the first init from file name takes a Java string and returns a Boolean type. And it takes so all of these types are already Java. This is not your C bool or C++ bool. This is the Java type, and you can say public static native. So this is already usable by the developers who are working on your target platform. So if you have a mobile developer that specializes in Android, they can already use this. However, as I mentioned, this is relatively low level because we're kind of threading everything through a very primitive interface. So one very important thing, and it's very easy to not do this in your project, but I think it makes a world of difference, is the last layer, which I call it the interface wrappers. So this gives us a high-level wrapper for the native interface, the native import layer. It gives the more natural, more familiar, I knew the animation is going to catch you. You have to listen to me. So it's much more natural, much more familiar syntax, much more typical idioms for the target platform, right? So I'll show you an example and you see exactly what I mean in a second. So again, here we can look at integration tests. And in this case, again, these tests are going to show you how the user is going to use your API. And again, it depends on the context. It depends on the actual target. So this example uses a slightly different set of functions just to make the point. So again, it's an Android example. I'm importing the Android graphics pointf type. And again, I'm loading some kind of DLL called native face detector. This is the JNI shared object library that I built with C++. And I'm using the import. I'm importing the function. You can see it's called getFaceCenterPoint with the lowercase g. So this really just reflects the underlying DLL function. And you can see that the return type is an array of 2 floats, right? So that's not exactly what you would expect if you were expecting maybe the center of the face to be a point or an XY position. Returning an array of 2 floats really isn't the most convenient interface, but it is the only thing that we can pass from such a native DLL. So at this layer, what we're doing is we can add another function, which again, it's just a simple wrapper over what we had before. I can call it get face center point, and this now it's with the uppercase G, as is the convention in Java. And this, in this case, it's returning, the return type is pointf, which is what Android developers expect. And all we're doing really is calling the function, the native function, and creating a new point. Now this might seem kind of excessive, and okay, you know, maybe the developer, they can handle my lower level APIs, but in fact, this is how Android, the whole Android ecosystem is implemented. So most of this, the API and the SDK, the Android SDK that you get to use when you're writing an Android app, uses exactly this type of idiom. It's Java types wrapping underlying C++ code or C++ system code. So although it seems kind of esoteric at first, but then you realize that every Java system call you've ever used really calls some kind of underlying Linux or C function. So to summarize, in the cross-platform C API and the boundary interface layers, we create some kind of C-style wrappers for the C++ API. And this really entailed going to a lower level code with less expressive syntax and weaker types. And as we all know, the weaker the type system, the more bug-prone our code is going to be. Now, at the native interface layer, what we did, we had the opportunity to undo all of that weakening and lowering of the type safety and the expressiveness and restore order. So we can wrap the low-level code with higher-level functions and types, although we have to do that on each of our target platforms. We also expose the interface and it feels much more natural. And those developers that are specialized in each of the particular target platforms can now feel extremely comfortable in using our platforms, making our code much safer and more plausible to actually be used, you know. Now, as I said, you won't necessarily be using each of these layers like as separate files or separate builds. This really depends on your specific project. It depends on the variety of platforms that you're targeting. But the aspects still remain. And the better the separation that we can make, the more likely it is that you'll be able to refactor it sooner, fix bugs on more platforms simultaneously, and easily maintain them, right? So we still have a little bit more time. So I want to go over a quick example. So as some of you may be familiar with the Party Parrot, right? I saw this animation some time ago, and I said, you know, I came across where this came from. It's actually a real parrot from a documentary about these endangered New Zealand parrots. And somebody just took the video and made this really cool animation. And I thought, I wanted to see how we can play with some cross-platform code. And I decided, okay, let me take the video, the actual video clip, and see if I can generate this a similar video to this animated GIF. So I chose OpenCV. That's an open source computer vision library for image manipulation. And I wrote a single function in C++, or in fact, in this case, it's just it's a standalone free function. So you might say it's like the air quote C. There's no objects here. I call it rotate hue. What it's going to do, it's going to receive a frame. That's the first argument, a 3-channel RGB image, and then it's going to convert it from the RGB space into the HSV space, a different color space. It's going to do some kind of twist on the color, and then return another image that can be displayed. So we get the same effect of the color, the rotating of the colors. And we have a namespace color cycle. It has 2 functions, and the interesting one is rotate hue. It accepts 2 arguments. The first one is the input image. The second one is the output image. And it accepts a 3rd argument, which is the number of steps or the speed that this hue rotation is going to be. So if the number is small, if 0, the color is going to remain as it was before. And if it increases, that means how fast these colors, how bad is the party, right? And clear all is just going to clear up some storage. Now, in this case, this is what I call the cross-platform C++ API. And because this is just 2 standalone functions, I already combined them into a single, you could say this is also the Crossplatform C API. Although these are not really C types, but for my I had two targets in mind. I wanted it to run on Windows, which is the native place where OpenCV runs, and I wanted to target a new platform, the browser. So I'm going to put the conversions inside the browser specifically. So we come to our next layer. This is the boundary interface layer. Now, in this case, we expose an extern C function to rotate colors, and we have to add, now there's some mscript, and I'm going to use mscript. This is a project that comes from Mozilla that allows us to compile, it uses LLVM to compile C and C++ code into JavaScript, or a subset of JavaScript called ASM.js. Today, there's also a version that compiles to WebAssembly. The code would probably be the same, just somewhat different compilation flags, build flags. So we have this, excuse me. We have this flag called mscript and keep alive. Now, the thing is that in a browser, since our target platform is really the JavaScript engine of the browser. And JavaScript doesn't have any, when it keeps images, it keeps them in 4-channel RGBA. And the numbers are typically, there might be doubles. So there are some conversions to be made here. So I'm defining a new function called rotate colors. It takes, the first two arguments are the width and height of the image. The third argument is the frame coming in from the browser. And as I said, it's a 4-channel image. And the output frame is, again, another 4-channel image, because that's the only thing a browser can actually display. And all we have to do inside is now, but our original C function expected only a 3-channel image. So we have to do some conversions. We have to create these images. So in this case, I'm using, you can see global data. This is just an example. So your code might consider additional options. And really, the only interesting part of this code is the call to color cycle rotate hue, where we're passing the converted images in, including h steps, which is the speed that we're going to rotate the colors, and converting back to the output image to 4 channels. And we can build this. Now, this block of text, this is already running. We have to import our JavaScript. Okay, this code compiles to ASM.js. This is a JavaScript file that is not human readable. It looks like assembly. Or in WebAssembly, it is a type of assembly. So this is like a binary file. Now we need to load the result of this file into some kind of JavaScript application that's going to drive it. So not a JavaScript application, this is the native importer. So we need to expose the functionality of this function to the JavaScript environment. So in this case, most of the code is JavaScript and HTML related to buffer management. Basically, I implemented a kind of shared pointer here and memory copying. It's not really interesting. The only interesting part is the calling of module rotate colors. Module is the name of the object that mscript creates in the global JavaScript namespace. And it just gives us this nice function called rotate colors. We pass it the width, we pass it the height. We're getting the byte offsets from the image, the HTML image tag buffers for the input image and the output image, and we pass it the number of steps. All that's left to do now, we just wrote our last JavaScript code. All we have to do now is really write the host app. Now, the host app inside the browser is just the HTML page. So the HTML page looks something like this. It's a few lines of HTML. We place a regular video into the HTML, so it's going to just display the video. We load our JavaScript file. We load our ASM JavaScript file into the HTML. We create the object, give it the name of the file, and we create an HTML form slider that allows us to control the speed of the hue change, the hue rotation in real time. So we're basically setting up some UI elements and showing the results. So now let's see how this works. Now I have to drag it. Do I drag it left or right? Here we go. So this is a blog post I wrote about this subject. And you can see on the left, this is the original HTML video tag. So I didn't do anything. This is just give a video to put a HTML video tag. That's what it's going to look like. On the right, every time the browser is playing the video, it extracts the frame and calls our JavaScript code, passing it the buffers, the pixels of each frame. The JavaScript engine calls our code, rotates the hue, converts that back to the new image, and displays it on the screen. So as you can see, we're seeing the Party Parrot on the right. Now, just so you don't think this is a video, I can go to our slider, and if I move it to the left, you see that it remains the same hue. If I move it to the right, then the party gets, the parrot has more, I guess he had more to drink. Right, so I'll be happy to take questions. Just leave that.
Do you have any examples of callbacks between the language boundaries?
I don't have examples here. I will tell you that I have written some extremely complicated callback-based multi-threaded code that runs on both iOS and Android by injecting, by building a mirroring, for example, an object hierarchy from the C++ into both of these systems, and using like callback mechanisms that asynchronously create, for example, on the Android would create an STD thread inside the C++ would create a Java virtual machine thread, a new one, and inject the call over there. So it is possible. And the only reason I could actually manage to do that, because it is pretty technical, is because I have this separation of concerns. Because you know where you need to touch, and you know that no leaking of concerns happens. So it is possible to do some pretty impressive stuff. Yeah.
Okay, and the other question regarding propagating exceptions from Java to C. I guess it's feasible, but...
From Java to C?
Yes, so when you have a callback, let's say, that will be called from Java side to C side, then Java may throw an exception, and that could be catched.
Well, any Java code can call any function from your API. So if you have something you expose that's called exception handler, just call it from your Java code, right?
Yeah, it is rather using some Java native interface API. You can check if, let's say, some function triggered on Java side from an exception, and you can propagate it back to C or C++. So I was just wondering if you tried such a setup.
I don't think so. I haven't tried that.
Okay. And
you're welcome to check out the blog post. Most of this appears on, it's actually a couple of blog posts. This one is about having OpenCV run in the browser. There's another one describing exactly the Salami method, and there are more details there. And you're welcome to reach out to me as well.
Okay. And one comment regarding Genie, since I tried that. It is not well applicable here, I think, because in your idea, we have this XC API where we write our own wrapper, and Genie produces C++ classes from some ideal, yeah. So you have there all these virtual functions and shared pointers. So I wouldn't use here Genie. I would rather use here just Swig, or maybe write it my own. Yeah. So thank you.
So question probably related to previous one. In your example, we already knew how much host platform has to allocate for output matrix. But what if we do not know until we complete an operation and we would like to pass the ownership of this object to caller? So basically it means that in our function we would like to use JavaScript allocator, put a result there, and pass it to caller. Actually,
This is exactly what I do with the parrot. I'm actually passing, let me show you. Oh. This is, if you look at the fifth, I think it's the fourth argument is passing the output bytes from the DOM tree.
yeah, but we already know how much we have to allocate.
No?
But
You mean that the C++ code generates this?
no. I mean,
calculates?
in your example, the output buffer is the same as input buffer in terms of size.
Yes.
But what if we do some decompression? We don't know, and we don't know what will be the size of the result.
It's not a problem because unless you're exceeding the mscript and memory space, you have this memory. This is a regularly managed memory in C++, and you can get a pointer to this memory. You might need to copy it into some kind of, to a JavaScript buffer, but you already, at that point, you already know the size.
Yeah, but how can I allocate JavaScript buffer within my
Well,
C++
The last
function?
time when I wrote this, mscript couldn't actually share memory buffers between the browser and the C++ code. So you have to copy anyway. That's what most of this code does, is really allow you to do the minimum number of copies. So in that case, at the point where you need the memory, you need to return the memory. You say JavaScript, okay, give me a typed array, and you make the copy there.
Did you experiment with using host allocator within your C++ application? Like OpenCV
No,
actually
it wouldn't
uses.
work here because you cannot share the code. So it's not relevant.
Yeah,
For this particular example.
OpenCV does this by linking to Python DLL.
Okay, you can show me later. Okay.
Thanks.
Hi. So I think this is a good example, like this JavaScript example of when we have some control implemented in different language than C++ with some UI or etc. And we are calling asynchronously some business logic in C++ layer, which is cross-platform, and then we need to pass it back as a callback. So callback is some kind of classic examples. So I have several questions here. So one question for the callback. Some people mentioned DGNI here. So you know that DGNI, it allows to pass somehow callback between different layers. But there is some concept of future, which I don't think is supported by DGNI, but it's some, you know what future is in STL layer.
Yes.
So is there any way actually to expect that something better than callback will be supported between different platforms in future, like this future concept?
I think it depends on the target platform. For example, I wrote, let's say you're targeting not the browser, which is a kind of different type of ecosystem, but let's say you're targeting iOS and Android. So in that case, both of them are actually running a Linux underneath, right? They're running an operating system which is a binary. It uses C++ anyway. And you can use stood thread, which means, and you can use futures, you can use promises, you can do anything asynchronously. The only place you need to actually do the ugly stuff is where you're trying to interface with the external system. But that works. So I'm not sure it answers your question.
Kind of. And another question is actually about callback. Two questions about callback. So first question is, one of the challenges is between different, let's say, languages, if we're calling some callback, we need to pass some data or some parameters or conversion of this data. So that's on one, and there is actually multiple way to do it. So the one way is just to signal and pass some handle, which could be just object, and then this code from, let's say, from JavaScript, when we'll call synchronous some other method to obtain results, and it will be flexible because some data object or structure can be different. So what you can recommend in this case?
I think JavaScript is a different system, so I'm not sure everything you can do in C you can do in JavaScript, but we have 20 seconds left, so maybe you catch me later.
Okay.
And you have 19 seconds.
I just have a quick question about refactoring existing code that already is monolithic and like this. And if you wanted to do this, to break this up into different layers of a whole C++ stack right now, and you wanted to start doing this, how would you go about doing? Like, what would you expose in the C API? How do you decide what to do there? If you, let's say you haven't separated UI and core already, that's tough.
My dad would say it's like hedgehogs make love.
Very
Very carefully.
Yeah. All right. Thank you.
Thank you.